So here we have a single cell intended to operate in D mode, configured as a 1-bit adder. Two input bits A and B come from the north and south, a carry in comes from the east, and the carry out goes to the west. And the equations are well defined in digital logic. The sum is just the exclusive OR of the three inputs. The outgoing carry is the AND of any two inputs. And we don't need to worry about reducing these equations or anything, of course. We can just write a truth table that corresponds to these particular equations, and that completely defines the behavior of this cell as a 1-bit adder. But now we have a situation where if we take a number of cells sitting side by side, for example, these 4 cells, we can send in a 4-bit number through the top and a 4-bit number B through the bottom. And our carries will ripple from the output of one stage to the input of the next. And we get a 4-bit sum out of the bottom. And we can take the carry out from the final stage, and we can use one more cell on this row of cells to take that carry in and send it out to the south as a 4th sum bit. And there we have a 4-bit adder set up as an old-fashioned ripple carry adder implemented using 4 single cells. And again, this is just standard digital logic. There's nothing cell matrixy per se about doing this. This is exactly how you would design a ripple carry adder using 4 full adders. And in this case, a full adder happens to fit in one cell. So the tiling is quite natural because of the way the outputs feed from one cell to the inputs of the next. So we can lay this out. The nice thing is, if you wanted to make an adder of 128-bit numbers, you could repeat this pattern just out to 128 cells, and you have a very large ripple carry adder. Now, the propagation delay of a ripple carry is not something you want necessarily when you're adding 128 cells. But the idea is, if you have an atomic unit that you can repeat in order to scale up your design, this is an architecture that supports that very naturally.